Hello again, and welcome to our lecture on the trigonometric functions. Last lecture we looked at angles, and we talked about how to measure an angle. And I pointed out there are really two important ways to measure angles, either using degrees or using radians. And we also learned how to convert from one to the other. In applications, problems will often be in degrees or in radians, and we have to know how to go back and forth. Well, today I'm pretty excited because we're going to define the 6 trigonometric functions. And if you've never seen trigonometry before, this will be an eye-opening experience, I think. The 6 functions will be defined using what we call a right triangle definition. If you pick up a textbook on algebra and trigonometry, or a trigonometry textbook, or a pre-calculus textbook, about half of them will use this approach for beginning to define the trigonometric functions, and the other half of the other books will use a different technique, which we'll actually do next lecture. But right now, I think the triangle definition is a little bit simpler to understand. So let's do it. And to see how this works, we have to recall a very famous theorem, the Pythagorean theorem. Here I've drawn a right triangle, and I've labeled the two legs A and B, and the hypotenuse is labeled C, and the Pythagorean theorem says that A squared plus B squared equals C squared. Or if you want, C is the square root of A squared plus B squared. In fact, this is an if and only if theorem. If you see a triangle that satisfies that equation, then it's a right triangle. It kind of goes both ways. Some simple examples. If the sides are 3 and 4, then the hypotenuse is 5, and it's a right triangle. 3 squared plus 4 squared, 9 plus 16 is 25. Another right triangle has sides 5, 12, and hypotenuse 13. And there's an infinite number of right triangles having integer sides. Let me pause here and talk about a related equation related to the Pythagorean theorem, a very, very famous mathematical problem. The Pythagorean theorem says A squared plus B squared equals C squared for right triangles. And in fact, there are integer solutions to that equation. A equals 3, B equals 4, C equals 5. Let's change it. Instead of being squared, try cubed. A cubed plus B cubed equals C cubed. Are there any solutions to that equation where A, B, and C are positive integers? Well, mathematicians have tried for hundreds of years to find solutions to that equation. It's even worse. They changed the exponent not to 3, but to 4, or 5, or 6, or any integer, and they never found a solution. And this is called Fermat's last theorem. Fermat declared, hypothesized, that you would never find such a solution. That the equation A to the n plus B to the n equals C to the n, where n is bigger than 2, has no solutions. And this problem was finally solved in 1995 by a mathematician named Andrew Wiles at Princeton University. The proof took hundreds of years of many, many mathematicians working on it, and they finally showed there are no solutions to that equation. Okay, enough culture. Back to trigonometry, back to the important topic. How do we define the trigonometric functions? Well, let's look at our right triangle again. And the way you define it is, you assume one of the angles is labeled theta, and then we have the adjacent side, the side next to theta. We have the opposite side, and then, of course, I've labeled the hypotenuse. And here are the definitions of the 6 trigonometric functions. Sine theta is defined to be the length of the opposite side divided by the length of the hypotenuse. Opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Those are the first 3 trig functions. I like to say trig sometimes instead of trigonometric. It's a little shorter. And then we have 3 more trigonometric functions. Cosecant is hypotenuse over opposite. Secant is hypotenuse over adjacent. Cotangent is adjacent over opposite. Okay, 6 trigonometric functions. Those are the 6. Notice some properties already. The cosecant is the reciprocal of sine. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. So if you know the first 3 trig functions, you can get the other 3 by just taking reciprocals. Let's do a quick example. Let's compute some trigonometric values. And how about the following triangle? It's the 3, 4, 5 right triangle. So the angle theta is in the corner, and the adjacent side has 3 units, and the opposite side is 4 units, and of course the hypotenuse now is 5 because it's the square root of 3 squared plus 4 squared. It's our famous 3, 4, 5 right triangle. So what's the sine of theta? Well, it's opposite over hypotenuse, so it's 4 over 5. What's the cosine of theta? Adjacent side over hypotenuse, so it's 3 over 5. How about tangent? Well, tangent is opposite over adjacent, 4 over 3. Let me point out something here. Look at sine and cosine. Sine divided by cosine is also 4 over 3, isn't it? In fact, tangent can be defined as being sine divided by cosine. That's equivalent to our definition. And then the other 3 trig functions are pretty simple. They're the reciprocals of what we just calculated. So cosecant is the reciprocal of 4/5, so it's 5/4. Secant is the reciprocal of 3/5, so it's 5/3, and cotangent is 3/4. Well, congratulations. You just calculated trigonometric functions. You just calculated trigonometric values. Way to go. If you've never done it before, it's kind of feels good, I think. We've noticed those reciprocal relationships. Knowing a few of the trigonometric functions, you can get the other ones using those first few. And I've also pointed out one of the key facts that tangent is sine over cosine. Well, let me point out something else that's really fundamental. Very, very important. Go back and look at sine theta. It was 4/5, and cosine theta was 3/5. Well, what's 4/5 squared plus 3/5 squared? That'll be 16 plus 9 in the numerator, 25 in the common denominator. It's equal to 1. What do we have here? We have sine squared plus cosine squared equals 1. That is the most fundamental identity in all of trigonometry. If there's one fact about the trigonometric functions you want to take away after this lecture, it's the fact that sine squared theta plus cosine squared theta equals 1. Now, there's a notational issue that comes up here. If you look at a textbook on trigonometry, you won't see sine theta squared with the parentheses around the whole thing and then squared. What you'll see sine squared theta, and the same with cosine, etc. Powers of the trig function, they put the power right next to the word and before the angle. That's just the way it is. Don't blame me. That's just the way it is. Clearly, both methods are correct. You can write either one you want, but most scientists will write it that second way, sine squared theta, not sine theta squared. Okay, that's just a little notational device. What's the history of trigonometry? Well, it has a long history, but it seems that Hipparchus in the 2nd century BC, a Greek mathematician, was the first one to sort of develop trigonometric ideas. And he constructed tables similar to the trigonometric tables you'll see in backs of some textbooks. And he used these tables to track the planetary motion, the movement of the planets in the sky. And speaking of these tables of trigonometric values, if you have an old textbook on algebra and trigonometry, look in the back of it and you'll see tables of trigonometric values. In fact, you'll also see tables of logarithms, because in the old days, there were no calculators. So if you had to calculate the logarithm or the a trig function of some obscure angle, you had to use these tables. When I was a student, we didn't have calculators, and we became very proficient in using these tables to estimate values of trigonometric functions and logarithms. That world has ended. Textbooks are skinnier now because they've removed those tables. All right, let's do an example. Let's try another important triangle that occurs a lot. Let's find the sine, cosine, and tangent of a 45-degree angle. Remember, 45 degrees is the same as pi over 4 radians, and we can work in either units. So how could we find the sine, cosine, and tangent of 45 degrees? Well, let's draw a triangle. It'll be a right triangle, and if the angle we're interested in is 45 degrees, then the other acute angle is 45 degrees because the sum is 180 degrees. And if we make each side, each leg length 1, then we know the hypotenuse would be the square root of 2. 1 squared plus 1 squared, all square rooted. So this triangle looks like the picture. The two legs are 1 and 1, and the hypotenuse is the square root of 2. So let's do the computations. The sine of 45 degrees is the opposite over hypotenuse, 1 over square root of 2. Cosine is the same, isn't it? Adjacent over hypotenuse, 1 over square root of 2. And how about tangent? Oh, that's just opposite over adjacent, or 1. Or you could say sine of 45 divided by cosine of 45, and that's the same. It's 1. Let me point something out here you might have noticed as we've been going along. The sine of any angle, or the cosine of any angle, is less than 1 in absolute value, isn't it? And why is that true? Because it's a quotient of a leg divided by the hypotenuse, and the hypotenuse is longer than the leg, so that fraction is less than 1, isn't it? That will always be true. Okay, good going. How could you verify that answer you just calculated? We just calculated that sine of 45 degrees was square root of 2 over 2. And suppose you're taking a test or something and you want to see, hey, did I get that right? Well, one way to do it would be to use your calculator. As I said, the trigonometric functions, the keys are built into all scientific calculators. And if you punch in sine of 45 degrees, you'll get the following decimal number approximately, 0.707.106.781187, and it might go out even longer depending on how many digits you want to show. Is that the right answer? Did we get the right answer? Well, calculate square root of 2 over 2 on your calculator. Surprise, you get the same decimal. Wow. Now, this brings up a kind of a funny thing that happens in classes sometimes. A student will be asked, what's the sine of 45 degrees? And the student will use a calculator and get that decimal expansion. But that's only an approximation. And remember, I'm one of these mean teachers that requires the exact answer. But my students are so clever now, they recognize that number as being the square root of 2 over 2. It occurs so much. So they get that decimal and they go, oh yeah, that's the square root of 2 over 2, I bet. And then they write down the correct answer. Good. Okay, so that was kind of a nice way to verify. Well, let me show you a you be the teacher problem now that I've probably seen 100 times in my, I've been in the teaching business almost 40 years if you count a graduate student, Peace Corps, and the University of Florida. So I've been out there a long time, and I see this problem, or this question, this issue, all the time. Here it is. You're teaching the class, and you've just calculated the sine of 45 degrees, and everybody's happy in the classroom, and then suddenly after class, a student runs up to you and goes, Professor, I didn't get sine of 45 degrees to be what you said it was. My calculator said that sine of 45 is 0.8509035. Professor, you must have been wrong, because the calculator never lies. What should I tell that student? Nicely, of course. Well, the calculator was in the wrong mode. It was in radian mode, and we were calculating sine of 45 degrees, and hence we had to be in degree mode. So be very careful on this. This is a common pitfall, being in the wrong mode, radian or degree. And as I said earlier, if you go on to take a calculus course, you'll set your calculator in radian mode. All right, let's do another example. Another very important triangle here, and some very important trigonometric value. These are worth memorizing. We're going to calculate the sine and cosine, and hence all the others as well, but I'll just focus on the sine and cosine now, of a 30-degree angle and a 60-degree angle. Let's see how to do that. And here's a nice way of doing it. Take an equilateral triangle of side length 2. And so the sides are 2, 2, and 2, and each angle measures 60 degrees. And now drop the altitude from the top vertex down to the base. And that forms a 30, 60, 90 right triangle, doesn't it? The base angle is 60 degrees, and the angle up at the top is 30 degrees. Now, if the hypotenuse is 2, we started with the side being 2, then that lower side is length 1. And what about the height, the altitude? How long is the altitude? Well, the Pythagorean theorem says that it has to be the square root of 3, because the square root of 3 squared plus 1 gives 4, which is 2 squared. So in this 30, 60, 90 right triangle, I know the sides. 2 is the hypotenuse, 1 is the short leg, and the square root of 3 is the longer leg. All right, so given this situation, we can now calculate the sine and cosine of 30 degrees and 60 degrees. It's very easy. What's the sine of 30 degrees? Well, look at the picture. 30 degrees is up at the top, and it's going to be opposite over hypotenuse, so it's 1 over 2, or a half. How about cosine of 60 degrees? Well, let's look at the picture again. There's 60 degrees down at the bottom. What's cosine? It's adjacent over hypotenuse. Whoa, it's also equal to a half, isn't it? Isn't that curious? The sine of 30 is the cosine of 60. What's the cosine of 30? Well, let's find out. 30 is up at the top. Cosine is adjacent over hypotenuse, so it's square root of 3 over 2. What's the sine of 60? Same thing. Opposite over hypotenuse, square root of 3 over 2. Curious, isn't it? Cosine 30 is equal to sine of 60. Do you see a pattern here? Do you see a pattern? What relationship do 30 and 60 have with each other? What's their relationship? Yes, they're complementary angles, aren't they? And here's another fact about trigonometry. Cofunctions like sine and cosine, tangent and cotangent, secant and cosecant. Cofunctions of complementary angles are always equal. For instance, you can check this on your calculator. Calculate the tangent of 50 degrees and the cotangent of 40 degrees. They'll be the same because 50 and 40 are complementary. The secant of pi over 3 will be equal to the cosecant of pi over 6 because pi over 3 and pi over 6 add up to pi over 2, or 90 degrees if you convert back to degree mode. So that's kind of a nice little fact about trigonometry. Study tip here, something that I encourage my students to do. Please memorize the values of the sine and cosine function for 30 and 60 degrees. In other words, pi over 6 and pi over 3. They're really important. Let me reiterate those formulas using radian measure. The sine of pi over 6 is 30 degrees. The sine of pi over 6 is a half. And the sine of pi over 3 is square root of 3 over 2. And conversely, the cosine of pi over 6 is the square root of 3 over 2, and the cosine of pi over 3 is a half. Those values come up all the time. All right, we've computed some values. We're just getting started with trigonometry. Let me talk a little bit now about that identity I said that was so important. Sine squared theta plus cosine squared theta equals 1. That's the fundamental identity. From that identity, you can massage it a bit and get a couple more identities that occur quite a bit in calculus classes and, of course, in pre-calculus. Here's what you do. Start with the original identity and divide both sides by cosine squared. Okay, so on the left you'll have sine squared theta divided by cosine squared theta plus cosine squared theta divided by cosine squared theta, and on the other side you have 1 over cosine squared theta. All right, simplify. What's sine over cosine? Tangent. So the first term is tangent squared theta. How about cosine squared over cosine squared? Duh, that's 1. And how about 1 over cosine squared? That's secant squared. Remember, 1 over cosine equals secant. So here's a new identity. Tangent squared plus 1 is secant squared. And you can do a similar trick. Divide both sides by sine squared, and you get a third identity. 1 plus cotangent squared equals cosecant squared. So the moral of the story is that first identity gives rise to 2 more identities that are also used quite a bit in calculus and pre-calculus. Let's do another example. This is kind of a fun example, I think, because we'll be able to check it with a calculator a bit. Let's find the sine of the acute angle theta if it satisfies the following property. Its cosine is known. Its cosine is 0.8. So we're trying to find theta, the sine of theta, knowing its cosine. So knowing the cosine, can you find the sine? That's what we're asking. Well, we can use that fundamental identity, can't we? Sine squared plus cosine squared is 1. So cosine is 0.8, so sine squared plus 0.8 squared is 1. And now solve for sine theta. You obtain sine squared theta 1 minus 0.8 squared. That turns out to be 0.36, and then take square roots, and we get 0.6. So the sine of theta is 0.6 when the cosine is 0.8. And then we could calculate the tangent and the cotangent if we so wanted. But a lot of times students will say, wait a minute, we have this answer that knowing the cosine is 0.8, we're able to get the sine, but what is the angle? I don't care what the sine is. I mean, that was the problem, to find the sine. But what if I really want to know what the angle was? What angle theta satisfies the property that its cosine is 0.8? Well, we don't know how to do that yet, but I'll show you anyway. If you have a calculator, there's a key called the inverse cosine. It's right above the cosine key. And if you use that button, you'll discover that the value of theta such that the cosine of theta is 0.8 comes out to be about 0.6435 radians. And if you do it in degree mode, you'll come out to about 36.87 degrees. Now that skill will come later when we do inverse trigonometric functions. So don't panic yet. This is getting ahead of ourselves. But again, people are sometimes curious. Can I actually figure out the angle knowing its cosine? And you can. All right. Let me talk a little bit now about simplifying trigonometric expressions. Later on, as we go through the trigonometric lectures, we'll come across equations or expressions involving trigonometric functions, and you'll often want to try to simplify them, make them look a little bit neater. Let me show you one that really simplifies a lot. Suppose you're doing some work and you come across the expression secant theta plus tangent theta all times the other term secant theta minus tangent theta. Can you simplify that? Well, some magic happens here. It's kind of fun. We can play with those identities and get some nice simplifications. Multiply it out. Secant plus tangent times secant minus tangent turns out to be secant squared minus tangent squared. Good. So far we got it a little bit better. But now remember that tangent squared plus 1 is secant squared. That was one of those identities. So I can replace the secant squared with tangent squared plus 1, and the tangent squares then cancel, and I finally get down to 1. That big expression I started out with collapses to 1. Amazing, isn't it? Really simplified. I find there's no doubt in my mind that 1 is simpler than the original expression. Okay, let's talk about calculators a moment. Early on when they came out, the University of Florida actually had a course on trying to teach students to use calculators because we were using them in some of our math classes and science classes. And then, of course, we immediately discovered that the students know much more than we do as professors on how to use calculators. In my experience as a teacher, I've really never had students come up to me and go, "Professor, I just bought a calculator, can you help me use it?" Now, they might make some subtle mistakes like that degree and radian mode issue I've talked about. But generally speaking, students are really good with calculators. But let me point out some things in trigonometry that'll be useful to you. First of all, how would you calculate, say, the secant function? You look at your calculator, there's no key for the secant. It's not there. In fact, there's only really a sine, a cosine, and a tangent. But cosine is the reciprocal of secant. So to calculate secant, all you have to do is 1 over cosine. Okay, so, and that's the same thing with cotangent. That will be 1 over tangent, and the same with cosecant. Good. I also invite you, if you have a graphing calculator, to practice calculating some values. We did sine of 60 degrees a few minutes ago. Do that also on your calculator. See if you get the same answer. I think it builds up a lot of confidence when you see your calculator getting the same answer that you're getting using pencil and paper. Some calculators give decimal approximations of the answer, and others actually give the precise answer. I have a fancy calculator that when I punch in sine of 60 degrees, it spits out square root of 3 over 2, the exact answer. Pretty impressive. Okay, let's do an application. This is one of sort of the standard applications of trigonometry. These are some of the first applications that were ever developed, I think. Suppose you're a surveyor and you want to measure the height of that tree over there. There's a big tree over there. And you're, say, 50 feet away from the base of the tree. And you have an apparatus that's called a sextant that can measure the angle that the ground makes with the top of the tree. And suppose that angle is 71.5 degrees. How tall is the tree? Don't make me climb up the tree and measure it. I can figure it out with trigonometry. All right, let's do it. Well, in that picture, what trigonometric function should we use? Well, how about tangent? Because tangent of 71.5 degrees is opposite over adjacent y over 50, isn't it? And y is what I'm interested in. So with that equation, multiply through by 50, and you get y equals 50 times the tangent of 71.5 degrees. I punch that in my calculator in degree mode, and I get approximately 149.43 feet. That's the height of our tree. Good. Let's finish off with some true-false questions. These are kind of fun. As I think I've said earlier, I love this kind of question on an exam. Very easy to grade. So, true or false? Is sine of 60 degrees times cosine of 60 degrees equal to 1? What do you think? Sine of some angle, 60 degrees say, times cosecant, 60 degrees. I hope I said cosecant. Sine 60 times cosecant 60. Is that equal to 1? Well, yeah, it is, because cosecant is 1 over sine, and they cancel. So that's a true statement. Here's a trickier problem. Is sine of 45 degrees plus cosine of 45 degrees equal to 1? That kind of looks like the fundamental identity, doesn't it? But it's not squared. And in fact, that's a false statement. Sine of 45 is square root of 2 over 2. The cosine is also square root of 2 over 2. That does not add up to 1. And finally, why have we said earlier that the sine of an acute angle is always less than 1, or the cosine of an acute angle is always less than 1? Do you remember why that's true? It's pretty important. It'll come up again in future lectures. It's less than 1 because it's adjacent over hypotenuse or opposite over hypotenuse, and the hypotenuse of a right triangle is the longest side. All right, good going. We've finished our first real lecture on trigonometry, and we've defined the 6 functions using this right triangle definition. Next time we'll define the functions a little bit differently, and we'll discover that we can define the 6 trigonometric functions for any angle, positive or negative. And in fact, these trigonometric functions will then be thought of as functions of a real variable, just like we had the exponential function or the logarithmic function. Well, now we'll have the trigonometric functions. So see you next time. Thank you.